This is EE300 Linear Circuit Analysis 2, Module 2, Video 5, Circuit Step Response. In this video, we'll review previous results regarding the network function. We're going to look at first-order step responses and underdamped second-order step responses. Then, as usual, we'll have a summary and some previews. So, to review, we've already seen the idea of the driving point admittance and the impedance, which is the ratio of the variables in the S domain at a terminal pair. So the input terminal or the output terminal. So the admittance is a ratio of the current in the S domain to the voltage in the S domain, and the impedance is the ratio of the voltage in the S domain to the current in the S domain, and those are arithmetic inverses of each other. We also have the idea of a transfer function, which is where you look at a terminal variable, a branch variable at one pair of terminals, and you compare it to the branch variable at another pair of terminals. So usually output relative to input, and these are in the S domain. We also saw that if the input was a form of an exponential with rate S0, then the output would have an exponential at rate S0, where the amplitude was scaled by the network function, the transfer function, evaluated at the frequency S equals S0. And then you would also get the natural response terms from the poles, and those would come from the denominator of H of S. You can find the differential equation from H of S by cross-multiplying the terms and interpreting S standing for d by dt. And so the frequencies of the exponentials that are always in the output are the poles, and those come from the denominator of the network function, and those come from the left-hand side of the differential equation. And then the zeros are the frequencies of exponentials that aren't in the output, even when they're in the input, and those come from the numerator of the network function, the roots of the numerator of the network function, and then also that comes from the right-hand side of the differential equation. So let's look at some step responses. Let's start with first-order systems. Here's our favorite first-order system, the series RC circuit, where we look at the voltage across the capacitor. So let's find the transfer function V2 of S over V1 of S. It's just a voltage divider. So we have 1 over SC over R plus 1 over SC. As usual, we clear out the compound fraction by multiplying by SC over SC to get 1 over S times RC plus 1. And then to see where the poles are, we factor out 1 over RC, and that puts that into the numerator. So you have 1 over RC over S plus 1 over RC, and that has a form alpha over S plus alpha. And this isn't the only network function, the only transfer function that has that form. We'll see others later. You'll see them on the homework. So let's just treat this as a generic thing, alpha over S plus alpha, where alpha in this case is 1 over RC. RC is the time constant, 1 over RC, which is alpha, is the rate. So we've got our network function, which is alpha over S plus alpha. We know alpha is 1 over RC. Let's find the step response. So V1 of t is a unit step. We can use a unit step. If we have a scaled step, then we just get a scaled output. So we multiply the network function times 1 over S. We can do our partial fractions to get the total response. We know that the amplitude of the over S term is going to be 1 because you plug in S equals 0 into H of S to get the amplitude of the drive function. And then to find the over S plus alpha term, you cover up S plus alpha in the denominator and let S equal minus alpha. And what's left, and you get minus 1. So then the time domain function is V2 of t is 1 minus e to the minus alpha t, all times u of t volts. You've seen this since circuits 1. You've seen it in physics probably. It's the step response of an RC circuit when you look at the voltage across capacitor. So you know what this is going to look like. It's a 1 minus exponential form, so it starts at t equals 0 with a value of 0. There's really a constant 1 there, and then there's a minus e to the minus alpha t. I didn't plot the separate components, but those add up to that standard step exponential shape of a 1 minus exponential. Okay, so let's say somebody gives you this graph and says, how would you find out the alpha? I mean, you know that it decays to 0, the exponential part decays to 0 over 4 or 5 time constants, but how do you find that time constant? You use the fact that for an exponential shape, if you draw the tangent to the line at any point, it reaches the final value 1 time constant later. So here, if we start at 0 and draw the tangent, that tangent is going to intercept the final value, which is v equals 1 time constant later, and the time constant is 1 over alpha. You can start someplace else like 2 over alpha, and again, it's going to intercept the final value 1 time constant later. You could also pick a couple of points and measure the values and then say, we know that's an exponential shape and determine the parameters that way. But you can always just take the tangent to the line is always going to intercept the final value 1 time constant later. Let's look at the same circuit, but now let's look at the output across the resistor. So what's the network function now? Well, R over 1 over SC plus R, again, multiplied through by SC over SC, so you get SRC over SRC plus 1. And now we clear out the 1 over the RC term, we get S over S plus 1 over RC. And that has the form S over S plus alpha. Alpha, again, is the rate. It's 1 over RC, just like it was before, except now we have a 0 at S equals 0. We already know from our knowledge of poles and zeros that the 0 is the frequency of an exponential in the input that's not going to be in the output. And a step function is an exponential with a 0 rate. So when we put the exponential in, when we put the step in, there's no step in the output. We just get 1 over S plus alpha for V2 of S, and V2 of t is just e to the minus alpha t u of t. So, I mean, that has to go with the 1 minus e to the minus alpha t for the voltage across the capacitor. They always have to add up to 1, the input amplitude, for t greater than or equal to 0. So when we look at that as a graph, we see the decaying exponential. The voltage across the resistor does jump to 1. The capacitor voltage stays 0. So the voltage across the resistor jumps up to 1 and then decays down to 0 as the capacitor charges up. We can do the same thing where you measure the slope to figure out the slope at any point is going to give you the time constant because it's going to intercept the final value one time constant later. We're going to be seeing more complicated circuits, but mainly voltage dividers involving R's and C's. That's going to be our biggest tool. We'll have some inductor circuits too. So here's one where we take the voltage across the resistor in series with the capacitor. So we go through the math as usual. It's R2 plus 1 over SC2 is the output voltage over the total resistance, R1 plus R2 plus 1 over SC. Clear out the SC terms. And then we're going to pull an R2C out of the numerator and an R1 plus R2C out of the denominator. The C's are going to cancel, so you get R2 over R1 plus R2. And then you have S plus 1 over R2C in the numerator over S plus 1 over quantity R1 plus R2 times C. If we identify, again, the rate in the denominator as alpha, and let's call the rate in the numerator beta, then we can recognize that the amplitude in the front, R2 over R1 plus R2, is really alpha over beta. That's just by arithmetic there. So now to find the output, what's going to happen? Well, first let's ask ourselves, looking at the waveform, looking at the circuit, what's going to happen? When V1 jumps up to 1 volt, there's still no voltage across the capacitor. But now, instead of showing up just across the input series branch, the voltage at the input is going to divide between R1 and R2. And that's that voltage divider R1 over R1 plus R2 at the amplitude. So how does that turn out here in terms of alpha and beta? Well, we do the math, we do the partial fractions. The amplitude of 1 over the over S term is still 1. The amplitude of the S plus alpha term turns out to be minus alpha plus beta over beta. You can just do the cover-up method to find that. So our output waveform is 1 minus quantity, 1 minus alpha over beta, e to the minus alpha t. It's a funny way to write it, but it has some value. So when we look at the waveform, we see that jump in the input there. This is R1 equals R2. They're both 1 k ohm, and C is 1 microfarad. But you can see that voltage jumps up when R1 and R2 are equal. You get half a volt initially across the output because you got half a volt across R1 and half a volt across R2. You can still measure the time constant in the same way, but looking at the decay portion, the decay reaches the final value one time constant later. Whether you start at t equals 0 or whether you start at t equals 2 over alpha. So first order circuits have constant plus exponential responses. You can really figure out what the response is going to be by looking at the circuit. You ought to be able to draw the graph and then figure out the parameters for the graph without ever really doing the formally having to do the Laplace transform, although it's great to be able to do the Laplace transform and show mathematically that what you intuitively have figured out is right. Alternatively, you may be thinking about doing it mathematically and then using your knowledge of circuits and the physics of circuits to understand whether the answer you get from your Laplace transform is right. Okay, let's look at the second order step response. We're only going to look at the underdamped case. You know there's the critically damped case and there's also the overdamped case. The overdamped case looks like two first order exponentials. The critically damped case is a t e to the minus exponential form we're not going to pay attention too much to those right now. Let's focus on the underdamped response. This is the most common form of the second order circuit, and it's got some of the more interesting properties. So we're going to look at the output across the capacitor. We could have also looked across the resistor and across the inductor, and you may do that on the homework. And let's find the transfer function between the input and the output. So again, it's a voltage divider formula. So 1 over CS over R plus SL plus 1 over CS. So we get 1 over S squared LC plus S RC plus 1. And then factoring out the LC, you get 1 over LC over S squared plus R over L times S plus 1 over LC. We introduce some notation. It should be familiar notation. It's used in circuits 1. We call 1 over LC omega 0 squared, where we call omega 0 the undamped natural frequency. And we call R over L 2 alpha, where alpha is called the damping. And we're going to introduce a new term here, zeta. And zeta is going to be the ratio of alpha to omega naught, the ratio of the damping to the undamped natural frequency, and that's called the damping ratio. So zeta is our damping ratio, omega naught is our undamped natural frequency, and we're going to write everything in terms of zeta and omega naught. Because zeta is a parameter that for the underdamped case is going to range between 0 and 1. That's what makes it underdamped. That's when you're going to get complex roots. And the roots then, in this case, are going to be where you used to have minus alpha, you're going to have minus zeta omega naught. And you used to have j root omega naught squared minus alpha squared. Well, we're going to pull the omega naught out, so we get j omega naught root 1 minus zeta squared. So you can sort of see, if you think about zeta and j root 1 minus zeta squared, that has a magnitude of 1. If you take the real part squared plus the imaginary part squared, you get 1. So those are on a circle. Those roots are always going to be on a circle, and the circle is going to have a radius omega naught. In our case, you can see where the real part is minus zeta omega naught, the imaginary part is j omega naught, 1 minus zeta squared. And you can see, sort of think as you change zeta to make zeta smaller, those roots are going to move closer to the j-axis, and the imaginary part's going to get closer to j omega naught. The real part's going to get closer to the real axis, the imaginary axis. And remember, the closer it gets to the imaginary axis, the slower the decay rate. The smaller the real part is, and the smaller in negative, the less negative it is, the slower the exponential decay. The bigger the imaginary part is, the faster the oscillation. So we can characterize that number there. We can see that they're on a circle, and we can identify an angle theta, which is the angle that the pole makes with the negative imaginary axis. It's not intuitive why we're doing that now. It shouldn't be intuitive, but we'll come back and use that a little bit. It's a handy thing to have. So you can see the tangent of that angle theta is going to be root 1 minus zeta squared over zeta. So how do we find the step response? We do it as we always do. We plug in 1 over S for the input. We write the natural, network function, the transfer function in terms of its roots. We've identified its roots. So the S in the denominator is the input S at the step function with a frequency of 0. And then you have the complex roots S with a minus zeta omega naught for the that S by zeta omega naught should not be there. Okay, so that's S plus zeta omega naught minus j omega. I thought I called all those, but apparently I didn't. So that should not be there. So it's just S plus zeta omega naught minus j omega naught root 1 minus zeta squared, and the second term is S plus zeta omega naught plus j omega naught root 1 minus zeta squared. The middle term is the root with the positive imaginary part, and the right-hand term is the root with the negative imaginary part. So we know we're going to write those as partial fractions, and again, the extra S should not be there. It ought to just be S plus zeta omega naught minus j omega naught root 1 minus zeta squared. And when you write complex roots with, you know that the coefficients, the residue, are going to be complex conjugates of each other. So we know the form of the answer before we even figure out what K naught and K1 are. So it's going to be K naught, the constant term, and then using what we learned early about Laplace transforms with complex roots 2 magnitude of K1, the exponential decay e minus zeta omega naught t, and then a cosine with a frequency omega naught root 1 minus zeta squared t. And then it's going to have the angle of K1 plus the angle of K1. It's a step input, so it's got a U of t in the output. We find h of K0 by just using h of 0, and h of 0 is 1. You plug it, you just get omega naught squared over omega naught squared. But to find K1, we have to do a little bit more work. So here's what you would get when you do K1. You've got that. The S is replaced by minus zeta omega naught plus j omega naught root 1 minus zeta squared in both the S term and the S plus term, if you will. So that's using our cover up, what we're left with there. So first you realize that in the right-hand term in the denominator, you've got a minus zeta omega naught and a plus zeta omega naught. So those cancel out, go away. And that leaves you with 2 omega naught root 1 minus zeta squared for the right-hand term in the denominator. And then you've got an omega naught squared in the numerator and an omega naught squared in the denominator, so you can cancel those out. And that leaves you with this expression, minus 1 over 2 root 1 minus zeta squared times 1 over root 1 minus zeta squared plus j zeta. You multiply through by the conjugate over the conjugate to get rid of the complex, the imaginary part in the denominator. And when you do that, you get minus 1 over 2 root 1 minus zeta squared times root 1 minus zeta squared minus minus j zeta. And then we're going to take the minus sign out front into the complex part. So we have 1 over 2 root 1 minus zeta squared, and that's the magnitude of this thing. Because remember we figured out that that something with a real part of root 1 minus zeta squared and an imaginary part of zeta has a magnitude of 1. So we're going to write this in magnitude angle form, and we're going to write the angle. The angle turns out to be pi over 2 plus theta, where theta is that angle we had earlier. So let's see where that comes from. So the number we're looking at is minus root 1 minus zeta squared plus j theta. And so we look at that in the complex plane. You see that it's in the second quadrant. And that angle that it makes with the imaginary axis, the positive imaginary axis, is the angle theta. That is, it's the angle whose tangent is 1 minus theta squared over theta, 1 minus zeta squared over zeta. So we can use that same angle theta that came from the pole location in our computations here. So we go back to our formula for V2, and now we know K1, we know K0 already, so K1 is 1 over 2 root 1 minus zeta squared, and when you plug that into 2 magnitude, the 2's go away. And so our formula comes out to be 1 plus 1 over root 1 minus zeta squared, e to the minus zeta omega naught t. That's the decaying term. That's the e to the minus real part of the pole determines the decay. And you have cos omega naught root 1 minus zeta squared, where that omega naught root 1 minus zeta squared is the damped natural frequency, the damped oscillation rate, times t. And you've got the pi over 2, and you've got the theta. And you know that cosine of something plus pi over 2 is minus sine of the something. So this is the way this is usually written. 1 minus 1 over root 1 minus zeta squared, e to the minus zeta omega naught t times the sine of omega naught root 1 minus zeta squared t plus theta. This is a common formula. It shows up in control systems. It's the step response of an underdamped second order system. It's parameterized by omega naught, the undamped natural frequency, and theta. And so we're going to look at some examples of that here in a second. So we're going to pick omega naught just equal to 2 pi, which makes the undamped period 1 second. So here's the first case when, again, it gets more oscillatory and slower decay as zeta decreases. So we'll start with zeta equals a half. You can see it's moderately underdamped. You get a little bit of what's called overshoot there, about 20% overshoot. It goes up to a peak, but it decays fairly quickly. And that's sort of, again, if you're thinking about things like the shock absorbers on your car, something you don't want to oscillate too much, but you also don't want it to be like a rock. You want it to have a little oscillation so that it can respond quickly. Then that's not a bad target to shoot for. The case where zeta is 0.1 is substantially underdamped, and you actually see now the decaying oscillations. You see that the rate of oscillation is about 1 second, so it's very close to the underdamped rate. And you see that it decays pretty close to zero. It's not exactly down to a zero within 4 or 5 cycles of the oscillation. There are parameters associated with this that we're not introducing today, that when you study control systems, you'll get, like the time to peak and the percent overshoot and the rise time and the settling time and stuff like that. That's not our point here today. We just want to get the sense of what these things do when you thump them with a stick. If we decrease the damping even more, so we have a zeta equals 0.01, then you can see you get very little decay within like 5 or 6 cycles of the oscillation, and you get a bigger peak value, and it takes it longer to decay. And so you can argue from looking at these examples that when zeta gets small enough, the poles are pretty much at minus zeta omega naught plus or minus j omega naught, that the root 1 minus zeta squares are not going to matter as zeta gets small. Right? Zeta gets small, zeta square is even smaller, so 1 minus zeta square goes to 1, and you can just ignore it. So this is basically the step. If you wanted to measure this and figure out what the parameters are, you could look at the 0 crossings to figure out the period of oscillation. You look at 2 0 crossings to get 1 period, and then you do 2 pi over the period to get omega 0. And then you could look at the damping from one cycle to the next. You look at the peak value and compare to the next peak value, and you would know the period, and you could figure out what e to the minus zeta omega naught times 1 period is to figure out what zeta omega naught is, and then you can figure out, you know the omega naught, so you can figure out zeta. We're not going to go through the exercise. You might do it on the homework, but it's just good to have a sense of how you could look at a graph. You get a graph, somebody comes in and says, I've measured this on the scope. How do I figure out what zeta and omega naught are? You say, oh, I can do that. I take the oscillation rate from the 0 crossings, or it's actually the crossing at the steady state value. If it's not really zeros there, it's 1, the steady state value that's decaying to. And then I look at the decay from 1 peak to the next, or from 2 peaks or 3 peaks, and figure out what that rate of exponential decay is. So we've looked, this to summarize, we looked at the step response of first order systems. It was always constant plus an exponential. Sometimes the constant value was 0 when you had a 0 at s equals 0. Sometimes the amplitude of the exponential was less than the amplitude of the constant. And you can measure the time constant by the fact that the slope, the tangent line reaches the final value 1 time constant later. For underdamped second order systems, we saw the damping ratio would be between 0 and 1. You get a sinusoidal step response plus the constant with the decaying envelope, but the transient part of the response is a decaying sinusoid. You can measure the period at steady state crossings to estimate the damped natural frequency, and you can measure the decay between successive peaks to estimate the rate of decay. So, I mean, you should get familiar with these things. You're going to see them in, mainly this is sort of a control systems point of view where you're concerned about the time rate of response of things and how much they wiggle. We'll have other issues when you deal with communication theory, and you don't really think in terms of poles and zeros as much in terms of an overall sense of frequency response. We'll talk about frequency responses in a couple of weeks. So what's coming up next, we're going to look at the impulse response. There's a video of the impulse response. And then we're going to look at designing these things. So how do we, given a network function, how do we make the circuit that will have that behavior? So this has been EE300 Linear Circuit Analysis 2, Module 2, Video 5, Circuit Step Response.